3D bioprinting, also just known as bioprinting, is a relatively new technology that, in theory, would allow humans to fabricate nearly any tissue or organ from scratch. The fundamental idea behind bioprinting is quite similar to that of ordinary 3D printing, in which a material, usually plastic, is printed, one layer at a time. Instead of plastic, however, bioprinters use bioink, usually composed of cells suspended in a special gel known as a hydrogel, which helps to protect, nourish, and hold the cells together. Some bioinks use a single type of cells, while others contain multiple types of cells, or multiple bioinks are used side by side, each with a different cell type. There are 3 categories of bioprinting that I will be discussing in this video, which differentiate in the method by which they turn the bioink into a specific shape. Note that due to the fact that this is an emerging technology, the exact name and classification of various methods vary from source to source. The concepts, however, are universal. I choose to group the various bioprinting methods into the following categories: extrusion-based bioprinting, droplet-based bioprinting, and energy-based bioprinting. Extrusion-based bioprinting is similar to what most people would think of when they think of conventional 3D printers. It involves forcing continuous filaments of a material through a nozzle in a controlled manner to create a 3D structure. The material is bioink, which, as I said before, usually consists of cells and a hydrogel. The filaments are forced through a nozzle by either pneumatic pressure, which is basically air pressure, or mechanically derived pressure, which comes from things like pistons or screws. The bioink must be stabilized quickly, or else it will not retain its shape. The bioink can be stabilized in a number of ways, largely depending on the hydrogel that is being used. As an example, during printing, the bioink can be stabilized by spraying a mist with a cross-linking agent dissolved in it. By the way, cross-linking just means linking one polymer chain to another, and this is done to stabilize bioink. In contrast, droplet-based bioprinting deposits discrete volumes or droplets of bioink onto a surface. Droplet-based bioprinting methods include inkjet-based bioprinting, microvalve-based bioprinting, and laser-induced forward transfer bioprinting. As with extrusion-based bioprinting, the bioink must be quickly stabilized in order for the structure to retain its shape, and the exact manner in which this is accomplished depends on the hydrogel being used. Inkjet-based bioprinting shares a lot in common with traditional inkjet printing. Here's how it works. At a high level, a pulse of pressure is used to eject a droplet of bioink. The pulse of pressure can be generated in one of 2 ways, using thermal mechanisms or piezoelectric mechanisms. In the thermal mechanism, a small surface of the bioink is heated and vaporized to create a bubble, which occupies a larger space than the liquid bioink did, creating pressure, forcing a droplet of bioink out of the nozzle. Once the bubble collapses, a bit of bioink is sucked from the reservoir, refilling the chamber, and the process is repeated. In the piezoelectric mechanism, an electric current is applied to a piezoelectric actuator, causing the chamber to deform slightly, forcing a droplet of bioink out of the nozzle. By the way, a piezoelectric actuator is a device that responds to an electric current by stretching and bending. Then, when the electric current to the piezoelectric actuator ceases, the shape returns to normal, and a bit of bioink is sucked from the reservoir, refilling the chamber, and the process is repeated. Next, microvalve-based bioprinting involves small valves that can be accurately opened and closed with electromagnets to deposit droplets of bioink, which is under pressure, usually pneumatic pressure, meaning air pressure. Laser-induced forward transfer bioprinting uses lasers to accurately position cells on a substrate or the place where the tissue will lie. Laser-induced forward transfer bioprinting consists of a laser, a focus lens, a ribbon, and a substrate. The ribbon could contain a sheet of transparent quartz glass with a very thin gold coating and a coating of bioink. When the laser reaches the gold, it heats it and greatly expands it, propelling a very small amount of bioink to the substrate, which will have been coated with hydrogel to dampen the kinetic energy of the droplet of bioink. This laser is quite precise, and hence this method is also quite precise. Finally, in energy-based bioprinting, a focused energy source, often a laser, is used to selectively solidify or stabilize a bioink. This method differs from extrusion-based bioprinting and droplet-based bioprinting in that the bioink is already in place. Perhaps the most notable method of energy-based bioprinting is stereolithography. In stereolithography, a laser is employed to selectively harden a small amount of bioink, which contains a light-sensitive hydrogel. This substance lies on a platform that is then moved away from the laser by a small amount. If, in doing so, the platform is immersed into bioink, then a fresh coat of bioink will flow on top of the now hardened layer of bioink, or if the platform has sidewalls, then a fresh layer of bioink can be coated separately. This process is repeated, eventually leaving you with a solid 3D structure once the liquid bioink is washed away. Each category of bioprinting has its own pros and cons. I won't bore you with all the specifics. However, as an example, laser-induced forward transfer bioprinting is precise and has a high printing resolution. Nevertheless, it is expensive, cumbersome, and time-consuming. Hence, different methods are used for different needs.